I'm Arundhati, and today I will be presenting our work on cost awareness in multi-agent active search. Autonomous robots have diverse applications ranging from rovers for the Mars mission to delivery robots, search and rescue operations, and even environment monitoring. These use cases typically deploy a multi-agent team of robots that can together achieve the intended task. If we look closely, in all of these applications, the robots ultimately have to search an unknown or unstructured environment to find their targets or goals. For example, the delivery robot needs to look around and navigate to the next destination, whereas the search and rescue robots have to find the human survivors in the environment. Motivated by these applications, in this work, we focus on the setup of active search. Active search involves online, adaptive, sequential decision-making to recover targets in the search space. We particularly consider scenarios where a team of robots, for example, the tree drones shown here, are looking for the targets in the search space indicated by these crosses. The number of targets is unknown, and targets are typically sparsely distributed in the environment. The agent's goal is to recover all of these targets as quickly as possible, that is, with fewer number of measurements. Agents follow a linear sensing model, where each agent receives a noisy observation, which is the ground truth, with some added measurement noise. Agents can sense a smaller area closer to the ground with higher accuracy, or they can sense a wider area at a greater height while receiving a noisier observation. Beta represents the flat vector form of the search grid. Xt is the sensing action at time t. So in this figure here, for the particular robot, its sensing action will be denoted by a vector of zeros and ones, with ones and these highlighted grid cells and zeros everywhere else. After executing this sensing action, the agent gets an observation yt that includes the measurement noise on account of the noisy sensors. Although it is common to have a central controller to coordinate among the agents in the multi-robot team, it may not always be practical or feasible. Communication channels can be unreliable. Synchronization may increase the idle wait time of some of the agents. In contrast with asynchronous communication, the agents can continue their search in the environment without having to wait for their teammates. So our work focuses on decentralized and asynchronous multi-agent active search. Additionally, we also want our agents to be cost-aware, so agents should recover all the targets while optimizing for the total cost incurred. We will consider two types of cost: travel cost, when the agent moves from location A to location B at a constant speed, and the sensing cost of executing an action. So in our multi-agent active search setup, agents have to recover all the targets while optimizing the total incurred cost. This is a multi-objective optimization problem where the two objectives are the reward for identifying targets and the cost for the sensing actions taken to do so. Prior work in multi-objective optimization uses scalarization to form a single weighted optimization objective, but the weights are context dependent. They might scale different units or overlook multiple possible solutions. Another approach is Pareto optimization, which results in a set of Pareto optimal actions for different objectives, but it can be computationally expensive to maintain and update the entire Pareto front. Additionally, prior approaches to multi-objective optimization usually consider single-agent systems and fully observable environments. In contrast, we consider the setting of multi-agent, multi-objective optimization under partial observability. We propose an approach based on non-myopic look-ahead reasoning about the reward-cost trade-off in a decentralized multi-agent setting. We propose a Monte Carlo tree search framework for look-ahead reasoning with Thompson sampling for decentralized multi-agent decision-making. We also propose a method for Pareto optimization with lower confidence bounds for computing the reward-cost trade-off for each cost-aware agent in active search. I will briefly describe how Thompson sampling can be used for multi-agent decision-making. Thompson sampling is an explore-exploit algorithm, and in prior work, it has been shown to be an efficient, decentralized, multi-agent decision-making algorithm. Starting from a belief over the environment, an agent can draw a sample from its current belief, and assuming this drawn sample to be the ground truth, it selects an action which maximizes a sample-dependent reward. In this paper, we extend this to the multi-step finite horizon look-ahead decision-making setup. Our algorithm, called CAST for Cost-Aware Active Search of Sparse Targets, is built on the MCTS framework. So at time t, an agent with a measurement set dt builds the search tree over m episodes. In each episode of tree building, a Thompson sample is drawn from the posterior belief at the root node. The root node is a belief node, and the tree has both belief nodes and action nodes. This is followed by a top-down pass denoted selection and expansion, and a bottom-up pass denoted backpropagation. In the top-down traversal phase of a simulation episode, a Thompson sample is first drawn at the root node. Then, assuming this sample is the ground truth in this episode, the agent simulates a sequence of action and belief nodes up to a fixed maximum depth. Reward and costs are computed at each action node, and the node visit counts are also updated. Once the maximum tree depth has been reached in the top-down traversal, the bottom-up pass begins. In this phase, the agent updates the look-ahead reward and cost values at each action and belief node visited in the top-down pass. Additionally, the Pareto fronts are also updated at each belief and action node using the lower confidence bound of the look-ahead reward and cost vectors. Finally, after m episodes of building the search tree, the agent selects the best action from its Pareto front at the root node. Once it executes this action and receives an observation, it shares that with its teammates and updates its posterior belief, and the process continues. Now, I will present some of our simulation results to evaluate this algorithm. We will use full recovery rate as our performance metric, which is the rate at which agents detect all the targets in the search space. We will consider two scenarios. First, when travel cost is higher than sensing cost, and next, when sensing is more expensive than traveling. We compare CAST to an information-greedy algorithm, RSI, a myopic active search algorithm called SPATS, and sequential point sensing, which exhaustively covers the search space. With different team sizes, 8 agents and 12 agents, as shown here, we see that CAST outperforms all the other baselines by recovering all targets with a lower total cost. Unlike the information-greedy method, Thompson sampling helps CAST agents not select the same action even when there is no central controller. Although the SPATS objective is designed for the setting when sensing cost is expensive so that the number of measurements should be minimized, we see that look-ahead decision-making, along with Pareto optimization, helps CAST outperform myopic, greedy SPATS agents. Next, we compare CAST with some cost-aware modifications of SPATS that we propose, using respectively scalarization and Pareto optimization with myopic Thompson sampling. We see that for different number of targets, the team of 8 agents can recover all the targets at a lower total cost, or across both scenarios of sensing cost being higher or lower than travel cost. This further indicates the benefit of finite horizon look-ahead, even with Thompson sampling and Pareto optimization. So, to summarize, in our paper, we have proposed a cost-aware multi-agent active search algorithm in a decentralized and asynchronous setting. We show that look-ahead decision-making guided by Thompson sampling from the posterior belief, along with Pareto optimization over the multi-objective problems, helps CAST outperform competitive baselines from prior work. This is a QR code for some animations with CAST and the baselines. Please feel free to reach out with any questions.